All around us, charged objects are creating this invisible energy landscape. It's a world of unseen forces, of potential, that shapes pretty much everything. So, in the next few minutes, we're going to map out that world. We'll start with the simplest points and build our way up to complex shapes, giving you a whole new way to see the unseen. So this is our big question. We're about to go on a journey to actually visualize these energy fields. But we're not going to use confusing diagrams of forces pushing and pulling everywhere. Nope, we're going to see them as simple, intuitive maps of potential hills and valleys. And the key that unlocks this whole simple view is one really powerful idea. And that right there, the fact that it's a scalar, is our superpower for this entire explainer. See, unlike forces, which have a direction and need all that messy vector math, potential is just a number. That means if you've got a bunch of charges, you just add up their potentials. That's it. No angles, no components. This one little idea makes incredibly complex problems surprisingly easy to handle. Okay, so to see this superpower in action, let's start with the most fundamental arrangement of charges out there, the electric dipole. Think of it as the hello world of charge distributions. It's the basic building block for understanding everything from water molecules to radio antennas. So here's our setup. A positive and a negative charge, kind of stuck together. We want to figure out the potential at some point P along their axis. Now notice the geometry here. The distance from our point P to the positive charge is r minus a, but the distance to the negative charge is r plus a. These different distances are the whole key to the calculation. And here's where our superpower just makes life easy. We don't need any complex geometry or vectors. We literally just take the potential from the positive charge and add it to the potential from the negative charge. It's really that simple. The math here just follows directly from the picture we just saw, right? The potential from the positive charge that uses the distance r minus a, and the potential from the negative one uses r plus a. It's a perfect one-to-one translation. After a little bit of straightforward algebra, the whole thing simplifies down into this beautifully compact formula. We've even bundled the charge and the separation into a single value p, which we call the dipole moment. It just neatly captures the dipole's essential character. Okay, so we've nailed the axis. But what happens if we look at the equatorial line? The one that cuts right through the middle, perpendicular to everything? Well, as you're about to see, the symmetry here creates a totally different and, frankly, a much, much simpler result. Just look at this geometry for a second. Any point on this equatorial line forms this perfect isosceles triangle with the two charges. What does that mean? It means the distance to the positive charge is exactly the same as the distance to the negative charge. This perfect symmetry is about to give us a really elegant result. And there it is, 0. A big, fat 0. Why? Well, because the point is the same distance from a positive charge and an equal but opposite negative charge. Their potentials are equal and opposite. They just perfectly cancel each other out. The entire equatorial line is a line of 0 potential. It's just beautifully simple. So we've handled discrete points, which is great, but the real world is full of objects where charge is smeared across a surface or all throughout a volume. So how does our scalar addition superpower handle that? Let's take on our next challenge, a continuous distribution of charge. We'll take a total charge, let's call it Q, and spread it out evenly around a thin ring. So how do we solve this? We use the exact same principle as before. We just break the ring into a bajillion tiny little point charges. We'll call them dq. And here's the beautiful part. Every single one of those little charge elements is the exact same distance from our point P on the axis. And because every little dq is at the same distance, we don't even need to do any complicated integration. We just add up all the little dq's, which gives us the total charge, Q. And we end up with this single, totally straightforward formula. The potential only depends on the total charge and that one common distance. All right, let's raise the stakes. We're moving from a 1D ring up to a 3D sphere. But not just one sphere, we're going to put two types head-to-head. A hollow shell, where the charge is only on the surface, versus a solid sphere, with charge distributed all the way through. This is where it gets really interesting. Okay, for the hollow sphere, that surface is a really clear boundary. This means we've got two totally distinct regions to think about, and the rules for calculating the potential are going to be different depending on whether our point P is outside the sphere or if it's inside. And here it is. This is one of the most important and honestly, kind of surprising, results in all of electrostatics. Once you're inside that charged shell, the potential doesn't change at all. It's a totally flat energy landscape. The potential at the very center is exactly the same as the potential right there at the surface. Now, let's look at the solid sphere. Because the charge is distributed all the way through it, the situation changes completely. Unlike the hollow sphere, the potential inside is not constant. As you can see from the formula, it depends on the square of your distance from the center. It actually changes as you move around inside. This table just puts it all together beautifully. Look at this. When you're outside either sphere, they are completely indistinguishable. They both behave exactly as if all their charge was crushed down to a single point at the center. But the second you cross that surface, their true natures are revealed. The hollow sphere's potential just flatlines, but the solid sphere's potential is actually highest at its very center, 1.5 times the potential at its surface. These formulas are powerful, for sure, but to really get a feel for them, we need to see them. So let's plot these results and actually visualize the energy landscapes we've just spent all this time calculating. On the left, you've got the hollow sphere. On the right, the solid sphere. These graphs are basically a visual summary of everything we've just figured out. They show the potential on the vertical axis versus the distance from the center on the horizontal axis. So let's break it down. For the hollow sphere, you see that perfectly flat potential inside. It's like a plateau, which then starts to drop off once you hit the surface. For the solid sphere, the potential starts at its absolute peak value at the center and then curves down like a parabola until it hits the surface. And notice, once you move past the radius A, both curves just merge together and become identical. They both behave just like a simple point charge. So there you have it. We've mapped these invisible energy landscapes, turning some pretty complex physics into simple hills and plateaus. And it all started by realizing that potential is just a number, a scalar, which let us simply add things up. That one idea is the key. Because if you know the shape of this landscape, you know everything. You can predict exactly how a charge will move, which way it's going to roll, and how much energy it'll gain or lose. And that is the true power of potential. It's not just a map of energy, it's a blueprint for motion.